Yeah. Now this TV did not turn off all day. So if it turns off now, the problem is you. Not me, not the TV. Okay. We did this. W equals QV. And then I said P equals IV. And then I said you can use the VRI triangle to write them in the different forms. Now we're continuing from here. What about capacitors? So last time we had our formulas. Just a quick recap. Work equals QV and power equals IV. And we still have our VIR triangle. But this is for a resistor doing some work.
Work is heat?
Well, maybe for my example work is heat, but it could be light, sound, whatever. What about capacitors though? It's a different story here. When a current is running through a resistor, initially there has been no charge passed through, until at some point there is a charge Q. All the time the voltage stays constant. Now see, that's a key difference. For a resistor the voltage stays constant. For a capacitor the voltage decreases. Let me graph voltage against charge. Okay, so you'll need this. Here's our resistor. And let's imagine we measure the voltage. And let's say we measure the current. And the current here, we'll just say, we'll keep it easy, we'll say it's 1 amp. Which means 1 coulomb per second. Yeah, and the voltage, we'll keep it easy, we'll say it's 1 volt. Which you might remember is 1 joule per coulomb. And what I want to graph, I think I said it here, didn't I? Voltage against charge. So I'll put V here and Q here. Now this might seem like a kind of a silly graph because every time 1 coulomb travels through the resistor, the voltage is constant. It's always 1. Yeah? So at the beginning, when only 1 coulomb has travelled, the voltage is 1. Yeah, constant. Now, when another coulomb travels, when 2 coulombs have travelled, how much is the voltage? It's still 1. No matter how much charge passes through the resistor, so even though we're getting more and more charge coming out at the end, we still have the same voltage. Okay? Now if I graph this, what's the area here? The area is, well let's just look at the formula. It would be, let's look at the unit. So what unit is volts? It's joules per coulomb. And what unit is charge? It's coulombs. So what's the unit here? It's joules, which is work. So in other words, the area on this graph is equal to the work done by the resistor. Now, you saw a moment ago I said the formula for work is QV. That's true. But if we want to be more general, it's not that... Okay, let me... I want to get red, make it important. Not work equals QV, rather work equals the area on the V, or I'll just write on the QV graph. Now, if it's a resistor, this will be a straight line. And because it's a straight line, the area will be just Q times V. So, for a resistor, this will actually equal Q times V. But technically, it's the area that is how much work the resistor has done. Okay? That's important. So I need you, I think it would be good if you could copy this down, and then we'll have to look at what happens with a capacitor. You know, as I was writing that, I was about to write VQ, and then I wondered if it was QV, because then I realised we don't say a YX graph, we say a XY graph, but then I realised we don't, but we call this graph, what do you call this graph? Yeah, but if you were to give it the same sentence structure, you would call it a velocity time graph. Yeah, but some people still call it time velocity graph. So I'm not happy that there's one grammar rule for this. So to prevent confusion, we say V against T, because that has only one meaning ever, which is Y against X. But there isn't one, unfortunately, there isn't one universal rule. Do you say XY or do you say YX? I've never heard anyone say YX, but we do that here. So it's like, what do we do? I don't know.
But we plot V on the y-axis and Q on the other.
Yeah. Yeah.
We need charge, right?
V against charge, but it doesn't sound as nice to say it that way.
Yeah.
I think I'll have to Google this later to see if there's some grammar rule on it. Continue?
No money.
You look a little tired, and you look a little tired. Starbucks again? Are you sure? Are you sure? Alright. And you?
Late.
How late?
Not late for normal people, but still late.
9 p.m.?
So,
For her, maybe.
that's like normally what time I sleep. But then I slept at 12 something last night, so nope.
Well.
I normally sleep at 9.
Okay. See, I was right then, 9 o'clock, yeah. Okay, got that?
Yeah.
Now, let's have a look at a capacitor. So, we have our capacitor, we measure its voltage, and also we have an ammeter, so we can know how much Q comes out at the end. Okay. Now, the voltmeter, the capacitor is a little bit different, of course, because firstly, if we were to look at the graph of V against T, what shape is this? It's like this, isn't it?
Yeah.
Exponentially decreasing. And we'll call this V0. And what about the Q?
Same.
Same, isn't it?
Yeah.
And that's Q there. Now, if I want to make this graph, I forgot, what do I put here? V and Q.
Oh.
Yeah? Let's see what happens here. Yeah, well, I think it might be linear, because you can say V equals V0 E minus, what's it, T over tau. Yeah? And you can also say Q equals Q0 E minus T over tau. True? If I divide these, what do I get? I get V over Q equals V0 over Q0. So, I can get V equals, I'll just call this a constant because it's V0 over Q0, so I'll call that M times Q. So it's like Y equals mx, that this graph will be a straight line. Yeah? So that means if I want the area here to get the work, I have a different formula. Work will be a half the base by the height. Now, how big is the base? Q. Or rather, Q0. This point here is Q0. How do I know it's Q0? I can probably see it here. It doesn't matter, trust me. Oh wait, did I do something backwards here? My graph is increasing. Yeah. Q over V. Q over V. Yeah, okay. A half Q times V. Yeah. Q0 is the charge at the start, and Q here is like the Q that's changing over time. But for the capacitors, when we use, for the capacitor questions, whenever I say charge, I always mean the charge at the beginning, because it's always changing. So when I say a capacitor is charged to 10 coulombs of charge, that always would mean at the beginning. So work is a half QV. So what's the only difference between this and the resistor formula? The half. Which I think I have here. I do. Oh, and of course you can make a change here with the. You can also use C equals Q over V. So you can get a second formula here. What does Q equal? CV. So this would be a half CV squared. These are the two formulas for work a capacitor can do when fully charged. So when charged to Q, that means the work it can do is a half QV under PD of V. Or you can write that as a half CV squared if you know the C and don't know the Q, which is more common actually.
What if you don't know the V? Can we...
Oh, that's a problem. If you don't know the V and the C?
No, you just don't know the V.
Oh, good. You don't know the V, but you know the Q and the C, maybe. That is a good question. I think it's still possible if you don't know the V. Yeah, so you have work equals a half QV, but if you don't know the V, you can say V is Q over C. So actually, you could get this formula. Okay, do you have this? Yeah? Yeah? Yes?
What do you mean when charged to Q under position?
Oh, I just mean the capacitor is charged up, so there's Q charge in it, and the potential difference if you were to connect it to a voltmeter would be V. Or if you prefer Q0, V0. Okay, you have that? No? I know, she's a bit slow today now. She must be tired too. What time did you sleep at?
12:30.
Okay. You normally sleep at 9, is it? Okay, you got this? Continue? Yep, okay, let's see. So, here's, we've got two questions here. So the first one, a 10 kilowatt oven is powered by a 220 volt electrical supply. What is the current here? Okay, so what formula could we use here to get the current? What can give us the current here for part A?
Power equals
P equals IV. So what could you say I equals? If P equals IV, then I equals... Okay, so calculate the I, please. Did you get an answer there? What answer did you get? 45.45. Yeah, 45.45. Or 45.5. Okay, so the first one here, if P equals IV, then I equals P over V, which is 10,000 over 220, which is 45.45 amps. Yeah? Right, what is the resistor? Okay, what formula can give me that? Yeah, V equals I or, isn't it? So or equals V over I. So that's 220 over 45.45. 4.84. Yeah. What's next now? How much charge has passed through the oven in 1 hour? So we can use the formula Q equals IT. So what's the current? 45.45, and the T? 3,600, yeah. 163.62 kilocoulombs. And lastly, how much work has the oven done? Now, you actually have a couple of ways to do this. You can use W equals QV, because you know both of these. Or you can also use the formula P equals IV, which equals work over time. So you can also say work equals VIT. Which would you prefer to use, QV or VIT? Yeah, why not? Because we already have the Q on the calculator still, don't we? So multiplied by, what did I say? 220, isn't it? Now that's a lot. Let me divide this. 36 megajoules. In Ireland, you pay per 3.6 megajoules. So for your electricity company, what they call 1 unit of energy is 3.6 megajoules. So this oven has used how much energy for the electrical company? Well, it's used 10 units. In Ireland, 1 unit is 3.6 megajoules. So this oven has used 10 units. I think 1 unit is about 15 cents. So if you think about it, that means this oven, which has been on for 1 hour, has used 10 of these. So that's 150 cents, €1.50. It sounds expensive if you do this every day, you know. And what did we say the shower cost? That was something like about the same, wasn't it? So take a shower and cook for an hour. That's €3. That's already €90 in 1 month, and that's before you charge up your phone or use your computer or anything else. Yeah. So it's the oven and the shower that use a lot of power. Continue. Yeah. Right. Now a capacitor example. A 120 volt charges a 100 millifarad. How much charge is stored in the capacitor? Alright, I want you to calculate that before I type it in. What's the charge here? So what formula could we use? Yeah. Yeah. Right, so first one you should have. What's the formula for Q? C, and what's C? 0.100, isn't it? Yeah. Over 120.
Yeah.
So the charge in the capacitor, that's tiny, it's 83 millicoulombs, 8.33 times 10 to the minus 4. Is that okay? That's the first one. Yes?
Why divided?
Oh yeah, it is. Dang. 12 coulombs. Okay. Part B.
Energy.
How much energy? Right, what formula can give me the energy here for the capacitor?
I know. 1/2
A half C V squared, isn't it? Yeah, a half C V squared. It's going to be pretty big. 720 joules. Yeah. Now, the next one is interesting. The capacitor is allowed to discharge through a 100 ohm resistor, which is actually a light. How long will the discharging take?
5 RC.
Yeah, it would take 5 time constants. Remember we said this is the discharge time, 5 time constants, 5 tau. But what's the formula for tau?
RC.
RC. So the time will be 5 RCs. Do we know R?
Yeah.
We do. And do we know C? We do. 5 RC. It'll take 50 seconds to fully discharge through the light. Yeah? Okay. Lastly, now, is the power of the light constant? What do you think? It's not. Because think about this. What did we say the formula for power is? IV. Okay. Is the V constant? No. And what's the formula for I? It's Q over T. Is the Q constant? No. So if the I is not constant and the V is not constant, is the P constant? No. In fact, what is happening to the P? Yeah, how is it changing? It's exponentially decreasing. But in part D, I say imagine roughly that it is constant. Now, in real life, it's not constant. It'll be brighter at the start and darker at the end. But I said, imagine that it is constant. Approximately, what's the power of the light? Well, roughly. Oh, I pulled it out. Where's my... There it is. Roughly, well, no, not roughly. The power, yeah, I'll say roughly, is the work, which we worked out earlier at 720 joules, that's how much work the light can do, divided by the time, which it's doing it for about 50 seconds. And that is a 14.4 watts. Now what does that answer mean? It means this. Here's the time, here's the power, and the power decreases exponentially. But if you were to imagine that it was constant, it would look something like this, that it's like an average of 14.4 watts. Now, again, I repeat, at the beginning it will be more than 14, and at the end it will be less than 14, but it's on average 14.4. So you could say the average power is 14.4. But in fact, the real power is actually a function of the time. And I would not be surprised if the formula had an exponential in it, because it's decreasing. Okay, so if you can add this one, please. This is the last part. Yeah?
Would you be able to find the other question, find the second?
When we study capacitors, we said that the time to discharge is roughly 5 time constants. The tau. Tau is equal to RC. Yeah. 5 tau, yeah.
Can we use the P for the P equals to P0 E power negative T over tau?
Did I give you that formula? No, I'm wondering, did I give it to you?
Or you gave it for the current?
Yeah, you see, I don't know if it does, because I feel like the P... I'll show you. If I equals I0 E minus T over tau, and V equals V0 E minus T over tau, then if I multiply these, I get P equals I0 V0 E minus 2T over tau. So I get P equals P0 E minus T over 2 tau. You see, I think the power might collapse faster than the I and the V on the graph.
You mean like it reaches?
Yeah, it will more quickly reach the x-axis on the graph. Because to get the P, I'd have to multiply these two together, and it makes a 2 here. I don't know, because they don't ask for the power in the exam. Isn't it 2 here because you multiply these?
What is P equals to P0 E to the power minus T over 2?
Yeah, that's a good question. Thank you. The 2 should be on the top. Because the 2 is on the top, it will make the power get bigger faster, which is what makes the graph get smaller quicker. Yeah, it's okay. Yeah. Okay, continue. Yeah. So I think that might be the last example. Yeah. So what I want you to do for a couple of minutes before we do the last topic, and then that's it for this semester, try 1 or 2 of these questions, and then we'll do the last topic, which is potential divider.